The emergence of general relativity prompted a new definition of both space-time and gravity. Through this new geometric representation, Einstein was able to describe and predict the behavior of any reference frame, regardless of its acceleration. However, further analysis of the equations of general relativity uncovered a rather bold prediction in which the laws of physics seem to break down: the singularity. A singularity is a point in which spacetime is contracted to a point of zero volume and infinite curvature, and therefore, time seems to stop. The ideas of general relativity cannot hold true within a singularity. These mysterious phenomena were predicted to exist both at the beginning of the universe before the Big Bang, as well as within the shroud of immense gravitational wells, which would come to be known as black holes. Formed when a star of a critical mass collapses in on itself to a point of extreme density, a black hole has enough gravitational force to trap anything, even light, which crosses its event horizon. Any singularity hiding within a black hole would be impossible to observe, as no information would be able to escape the unimaginable gravity. Therefore, the existence of singularities, and even of black holes, was an idea of great controversy throughout the 20th century, and demanded the attention of minds as great as J. Robert Oppenheimer and Roger Penrose. Following the acceptance of black holes, it became apparent that their nature may be unique. A black hole's concentrated mass necessitates the use of relativity to understand its gravitational interactions with the world around it, but Stephen Hawking discovered that they exemplify properties of quantum mechanics as well. Therefore, black holes became the first bodies to hold promise in uniting the opposing theories of general relativity and quantum mechanics into a single, unified theory of physics. According to Einstein's theory of general relativity, the universe can be represented mathematically by a four-dimensional continuum consisting of space and time. This is known as the space-time continuum. What made this theory unique is the utilization of non-Euclidean geometry, as Einstein recognized that Euclidean coordinate systems could not be preserved between non-inertial reference frames. The effects of gravity can be explained with this theory by assuming that this continuum is disturbed by the presence of mass. This relationship is defined by the complicated Einstein field equations. As spacetime curves around a body with mass, the lines of spacetime are then distorted around the body. This causes any other body moving through this spacetime to experience a pulling around and into the center of the original body, and thus the object accelerates. With this definition, it can be proven that gravity and acceleration are simply different manifestations of the same effect. Einstein developed this idea through the use of a thought experiment. He imagined a man falling off a roof. As this man falls, he does not feel his weight because he is accelerating towards the ground. Therefore, the man's acceleration must create a gravitational field which cancels out the field of the Earth. By taking this conclusion a step further, one could imagine a person inside a box, such as an elevator, moving in a straight line with constant velocity in intergalactic space. From the reference frame of the person, there seems to be no gravity. However, if an exterior string pulls the elevator and causes it to accelerate upwards relative to the person, then the person will feel a weight towards the floor. It would therefore be reasonable for the person to assume that the elevator possessed some sort of gravitational field, even though it is simply experiencing an acceleration. With these thought experiments, Einstein concluded that gravity and acceleration are equivalent, and therefore, a theory of relativity for accelerating reference frames could also serve as an explanation for the phenomena of gravity. Although the theory of general relativity was not published until 1915, the first predictions of non-luminous bodies came as early as the 18th century. Both Jean Michel and Pierre-Simon Laplace published their predictions of bodies with such great gravitational pulls that even light would not be able to escape. Jean Michel proposed that these bodies could be detected by analyzing the motion of bodies which surrounded them. A version of this method is still used today, as modern black holes can be found by analyzing the stars which orbit them. Similarly, Laplace claimed that the gravitational attraction of a star with a diameter 250 times that of the Sun and with comparable density to the Earth would be so great that no light could escape from its surface. The supposed nature of light would change dramatically in the centuries following these predictions, but it would not be until the era of Einstein that the gravitational effect on light would be proven. The theoretical discovery of black holes and singularities led to the development of the conjecture known as the weak cosmic censorship conjecture. This conjecture asserts that singularities are generally hidden within black holes, and thus naked singularities do not occur. This hypothesis was first formulated by Roger Penrose in 1969, and its importance lies in the philosophy of physics itself. Because we are unable to predict the effects of a singularity, the appearance of singularities outside the horizons of black holes would challenge the deterministic nature of physics as described by the general theory of relativity. General relativity assumes that as long as the initial conditions of a body are known, it must be possible to predict its future. This challenge against causality posed by singularities seemed to be a breaking point for general relativity. However, this breakdown is to be expected in such situations as a black hole, as the extreme conditions of black holes allow for the use of the theory of quantum mechanics. The formulation of quantum mechanics relies on the Heisenberg uncertainty principle, the idea that it is impossible to know the exact position and momentum of a particle. Our ability to observe the particle affects its trajectory, and thus in order to measure one quantity, we disturb the other. To resolve this challenge, quantum theory predicts the probabilities of each possible future state of the particle. This principle also challenges the deterministic nature of classical physics, as it assumes that the exact future of the universe cannot be known, only the probability of each case. The application of quantum theory to black holes opened the door for a new understanding of their behavior. It also provided a possibility for the unification of general relativity and quantum theory, as black holes exhibit both extreme gravity and extreme density. While most theoretical evidence agreed that black holes and singularities were inevitable in physically reasonable situations, it would take time before experimental evidence was provided. The first black hole, known as Cygnus X1, was discovered by Charles Thomas Bolton, Louis Webster, and Paul Murden in 1972. Cygnus X1 was discovered as part of an X-ray binary system, meaning the existence of the black hole was assumed from the accretion of matter from the closely orbiting star in the system as the black hole consumed the star. Much like the methods of detection predicted by Michel, this indirect observation has become a common way of discovering black holes. With that being said, the doubt which accompanied these methods of assumption were silenced with the release of the first image of a black hole in 2019. After collecting data from the center of the Messier 87 galaxy, the Event Horizon Telescope project released the rendered image of the black hole located within. The image features a bright ring surrounding a dark shadow. Although the event horizon is three-dimensional, this flat facade is created by the immense gravity curving the light around the horizon. Because of this effect, the black hole appears flat when viewed from any perspective. In addition, the light observed in this image is not actually visible light, but rather radio waves which have been rendered to represent a visible image. Experimental evidence of black holes also serves to confirm the theory of general relativity. According to this theory, the disturbance of space-time by matter causes the propagation of gravitational waves. Therefore, cataclysmic events such as the merging of two black holes should produce gravitational waves strong enough for us to detect. This is exactly what occurred on September 14, 2015, at the LIGO Gravitational Wave Observatory. Using a massive interferometer, the collaboration was able to detect the leftover waves produced from the merging of two distant black holes. From this observation, it was proven that the objects of extreme mass were less than 50 kilometers apart directly before the event. Therefore, these results clearly indicate that the bodies were stellar mass black holes. The combination of theoretical predictions and observational evidence led to the ability of physicists to determine the exact characteristics of black holes, removing the shroud from their previously questionable existence. According to the no-hair theorem, black holes can be characterized by three parameters, which can be measured externally: mass, electric charge, and angular momentum. However, this proposal suggests that any two black holes with equivalent values of these parameters would be indistinguishable. This conjecture is only applicable to idealistic black holes, and its validity is still an open theoretical question. Arguably the most notable characteristic of a black hole is the infamous event horizon. This boundary is defined by the Schwarzschild radius, and it is the point past which nothing can escape the gravitational force. In terms of general relativity, the event horizon is the point at which the deformation of space-time doesn't allow any paths out of the gravitational well. In addition, the curvature of space-time near the event horizon becomes so great that extreme time dilation takes over. According to an outside observer, anything falling into the black hole would seem to never reach the horizon, as the time is dilated to infinity, while the falling observer would measure time as moving uniformly. Past the event horizon, it becomes impossible to retrieve information about events as nothing can escape. This seems to challenge the idea of conservation of information and would become a serious challenge for black hole theorists. In contrast to all previously held beliefs of black holes, Stephen Hawking proposed his namesake Hawking radiation in 1974. He claimed that black holes emit an extremely small amount of radiation, which makes up a perfect black body spectrum. He came to this conclusion by utilizing the ideas of quantum field theory, which predict that quantum fluctuations from the immense energy of the black hole can produce these small amounts of radiation near the event horizon, meaning that some of the radiation can escape the pull. In other words, because the curvature of spacetime is so extreme, the density of the quantum field fluctuations becomes important where it would otherwise be negligible. This also implies that the mass of the black hole would be constantly decreasing, and thus the radiation would constantly increase. While the radiation is predominantly small and the evaporation of the black hole is extremely slow, the end of a black hole's lifetime would be a rapid and astoundingly bright process due to the accumulation of these effects. However, the lifetime of a black hole of solar mass would be longer than the current age of the universe, and thus black hole death is extremely rare. From their prediction by general relativity until their experimental confirmation, black holes have been surrounded by controversy. These mysterious entities reveal potential holes in the philosophical nature of physics. But they also hold the potential to unite our current knowledge into one theory of everything. With that being said, the intense nature of black holes makes them difficult to study directly, and it has taken the culmination of work from the entire planet to discover what we now know to be true about them. Therefore, while they may hold the keys to extending our physical knowledge, it will require great strides in both our experimental and theoretical capabilities. In other words, our understanding of the complexities of black holes and singularities has only just scratched the surface of the event horizon.